lecture 2 is all about network classification. Okay, so we said we just want to remind you of what a data communication system is a system that exchanges data over a distance, right? So we said we have major components, the medium, the sender, receiver, using a specific medium, the message that's being sent, and the protocol that they agree on. What is a protocol? It's kind of rules, guidelines that the sender and the receiver will agree on. Okay, example would be, you know, if you send me this message with this specific header and this specific tail, what does the head mean? What does the tail mean? What does the 001 mean? This is what we refer to as a protocol. Why? Because the sender and the receiver need to agree on this in order to communicate. And we're going to talk about different protocols as we go. Okay? So if you look at the different data flow of communication, we said we have three major kinds: the simplex, the half duplex, and the full duplex. The simplex, meaning it's one-way communication. A sends to B, again, like a mainframe or a computer sending to the monitor some information. This is one-way communication. The monitor typically would not communicate to the computer itself. It could be half duplex, which means two-way communication, like this, but one at a time. So it's half duplex, meaning you can communicate in both directions. A can communicate with B, and B can communicate with A also. That's what half duplex means. However, not at the same time. So one has to wait for the other to finish and then do it again. Said a good example would be fiber optics. Finally, a full duplex is the most common, where A could send to B and B could send to A using the same medium in both directions. Okay, and we will be seeing many of these as we go on in terms of examples. Okay. So again, the definition of a network is a bunch of devices, nodes, we refer to them. So we'll be using a lot of nodes from now on. So nodes like these are nodes, hosts connected to each other. This is what a network is, you know. How you connect them is what we refer to as the topology. So a network is a connection of devices, sensors, computers. We refer to them as nodes. These are nodes. Okay, and these are links, how they're connected. They could be virtual or they could be physical. Okay, so how do we classify networks then? Before we classify them, we define something called a subnet. A subnet is something I was drawing before. This is called a subnet, meaning excluding the computers. These are the computers, the PCs, or the devices, if you want to call them. These are the devices connected to the LAN and so on. When we connect them using routers, you can see these are routers, switches, you know, bridges, hubs. Everything here, this thing, is what we refer to as the subnet. And it's very important to know what the subnet is, especially in lecture 3. So next week, we'll be talking more about the subnet. But the subnet is connecting everything excluding the computers themselves. Okay? So that's what we refer to as a sub-network. A sub-network. Okay? So how do we classify networks? We classify them using 3 different techniques. 1, 2, and 3. Number 1 is what kind of technology for transmission am I using? Number 2 is how big my network is. So we classify them small, medium, large, X large, you know. And topology is how am I connecting them. So this is how big they are, size-wise. This is how are they connected. Connectivity. How are they connected? Okay. And this is what kind of technology am I using to transmit from the sender to the receiver or receivers. So let's start with number 1. Transmission technology. So transmission technology, we have three different kinds, either broadcast, multicast, or unicast. So one more time, broadcast, as you would expect, one to all. That's what broadcast is. I'm broadcasting, like I'm talking to all of you now. I'm broadcasting my message. When I talk to all of you, when I type on the chat, that's broadcasting to all. When I type to one of you, that's unicasting, you know? So broadcast is one sending to all. If you want to talk to one of them when you're broadcasting, everybody else will ignore it. But everybody else will receive it, but ignores. If I type on the chat, say, Fatima, come on, how are you? Everybody will receive my message, but only Fatima will look into that message. So we could broadcast logically or physically, again, using an IP address or a MAC address or a physical address. Okay? So you could broadcast with a local area network typically using a bus. That's what the most common thing. We're going to talk what a bus is when I talk about topologies. So typically a broadcast is something like this. I have something called a bus. It's like a big cable. Think about it as a big cable. I have computers connected to it. These are all computers. Okay? These computers are connected to it. Suppose this guy, A, wants to send to B. Okay? Typically, it's going to broadcast a message here. The message here will be sent. Would be received by this guy, and by this guy. They will ignore it because it's not their ID, and only B would kind of respond and do something with it. So that's what we refer to as a broadcast network, an example of it. Again, we said radio, satellite, these are typically all broadcasts, you know, TVs, channels, and so on. They're broadcasting. We are receiving. Again, it could be many to many as well, you know, many to many or one to many. Okay, that's what broadcasting is. Same logic is the multicast. Multicast, same like broadcast. However, I'm sending to a specified group. Okay, so we have a group ID, typically a bit, either 0 or 1. If it is 0, we say it is broadcast. If it is 1, it's a multicast. So that's going to be reserved to define if it is multicast or not. So that an ID, a bit, will define, am I using multicasting or not? So it's the same thing, but instead of me sending to everybody, I only send to a specified group using a group ID, a GID. Okay, that's how multicast works. A group ID. Now, finally, a point-to-point, which is the most common, unicast. It's point-to-point, as you would expect. Connection, we have nodes and links. So these are nodes. And they're connected with links. Not everybody's connected, depending. Suppose like this, you know. Could be like this. Okay. Suppose this is A. This is B. This is C. Suppose A wants to send to C. Then we go through the links. Using unicasting, it's going to go like this. If this is unicasting, or like this, right? This is how A would send to C. They're going to use B as a middle person, you know? That's what we refer to as unicasting. Again, most common. This is the most common, of course. This is what we use in the internet. Of course, right? Again, another word to it is point-to-point, end-to-end, you know, host-to-host. Okay, many terminologies for it, but typically it's point-to-point, the most common, P2P. Again, uses, to do that, we use protocols, you know, because we need to know which one is the best way, because A could have went like this, then like this, then like this, right? So there are many different ways to do it. So which one is the best way? So I need to find out which one is the best way. So I need to come up with an algorithm. This algorithm is what we refer to as routing. So in point-to-point, obviously, routing is very important. Routing is finding the optimal path. Not the shortest path, the optimal path. Because short doesn't always mean optimal. Okay, optimal meaning typically minimum delay, less traffic, all these criteria. I need to optimize the path that I'm choosing in order to deliver my message. Okay, guys? So the first technique is classifying by transmission technology. 3 different ways: broadcast, multicast, and point-to-point or unicast. You said unicast uses links. We need routing. Obviously, it decides on the optimal path compared to the others. Okay, so I have a couple of questions. Let's see. So large network tend to use what kind of transmission technology and why? That's question 1. And question 2, where do routing algorithm play an important role? Okay, broadcast, multicast, or unicast. Let's start with the number 1. Large network tend to use what kind of transmission technology? What do you think? In a large network where I'm sending a lot of information, do I broadcast, do I multicast, or do I unicast? What do you guys think? You broadcast, Fatima? You think? So if I have 1 million computers, you know, like the internet or more, even 1 billion, and one computer wants to send, you know, A wants to send to B. You think this A will broadcast to 1 million computers and everybody will ignore it except B until B gets it? Do you think that will happen? That's efficient?
I say multicast, right? The network can still be for.
What's that?
Multicast, that's what I'm thinking.
Okay, you take multicast. Okay, so of course it is, with no doubt, what? It is. It's obvious, right? I mean, you don't think I'm going to send to 1 million computers or 1 billion computers until one gets it, right? So what should I do?
Multi-class.
You send it to unicast. Of course, unicast. There's no doubt about this. I just told you guys. What's the biggest network that you know in life? What's the biggest? Internet, right? And I told you, in the internet, we use point-to-point. It's the most common. So, of course, large network tend to use point-to-point, you know, or unicasting. Because of obvious things. Why is the reason? Because of collisions. Because remember, if I'm sending a lot of packets, sending a lot of messages, they're going to collide. You know, they will collide with each other. And there's 1 million people receiving it. And again, it's very inefficient. Again, in an easy way for you to understand, imagine if I want to send an email, I want to send an email to you, I send an email to everybody, and everybody ignores it, but only you get it, you know? That would be so bad, right? So that wouldn't work. So that's kind of broadcast. Broadcast is very good for small network. I know you're thinking about radio, you're thinking about satellite, you're saying, oh, these are big networks, okay? So if you think about these are not big networks compared to other networks. Again, in these cases also, the goal was many to many to start with. That's why I wanted many people to receive my TV channel. So it was one antenna sending to many. Yes, this will work. In that example, yes, one sending to many and many want to receive it. So we all receive the channels. But if you wanted one to receive it, that would not work. And typically that's what we do when we talk about a network. Okay? So long story short, of course, large network use unicasting. The reason is collisions, traffic, efficiency, all the things I just mentioned. So where do routing algorithms play an important role, guys? Routing algorithms. So what is routing algorithms? If somebody wants to define it, I just said it 2 minutes ago. Is finding what? The optimal path. Yes, thank you, Muhammad Nihal. Bonus point for you. Finding the optimal path. So where is it? Where do we use it? Broadcasting, point-to-point, or multicasting? Yeah, so which one? Broadcast, multicast, or P2P? Fatima? P2P. Okay, P2P, Fatima. Bonus point for Fatima because she said unicast. So she said unicast already. So bonus point for you. Very good. Again, in broadcast, we don't need routing algorithm, right? No routing algorithm. Who can tell me why we don't need routing algorithm in broadcasting? Why we don't need routing algorithm in broadcasting? Yes, exactly, Muhammad. Yes, thank you. Because we are sending indeed to everyone. So there is no optimal path. And the path is basically everybody gets it. We're not going to one and the other. Everybody's getting it. Okay? Very good, very good. Any questions so far? Because I'm kind of moving slow. I've talked about some of these before, but if you have questions, now is the time for the first part. We're good? Okay, we are good. I guess I'm broadcasting my message to everybody, right? And everybody's receiving it. We are fine. I'm not doing point to point. If I'm doing point to point, only one of you will understand. If everybody understands, meaning I'm broadcasting. That's a good analogy, I guess. Okay, so let's move on. So the other technique is to classify networks by size. So we said 3 different ways of classification. Who could remind me? What are the 3 different ways of classification? We classify them by what, and what? Size, transmission technology, and topology. Thank you guys. Thank you. Thank you guys who are active. So I'd give Zain also a bonus point. Brooke, are you keeping track? Because Brooke is back, I think. And I think we had...
keeping track.
Yes, sir, both me and Brooke.
Yes, and we had Afrazali help me last time. So help Afrazali. Afrazali, share. If Brooke is not there, you'll be there, okay? But share with him what you sent me as well.
Okay, sure, sir.
Thank you. Let's move on. I'll send the class list by tomorrow or by next week, okay? So let's move on. Size-wise, that's the other transmission technology classification. So you can see we have PANs, PAN, meaning personal area network. We have LAN, local area network. And we have MAN, metropolitan area network. We have WAN, wide area network. And obviously the internet, we say it's a WAN at the end of the day, but it's kind of the biggest network out there, okay? So if you want to classify them by size, you could see. You can see that the PAN is the smallest. It's about 1 meter. About 1 meter. Could go a little bit bigger, but typically 1 to 2 meters. So what is a PAN? A PAN is basically a Bluetooth headset connected to your phone, connected to your smartwatch. We call this a PAN. Again, a good example would be a BAN as well. BAN. You know, BAN is what? Body area network, okay? So a BAN and a PAN, these are very small. Body area network meaning things connected to your body. It could be sensors to monitor your heart rate. It could be biological stuff as well. We refer to these as body area network. PAN, typically it's a bit bigger, where it includes, again, as I said, your headset, your smartwatch, your phone, things connected around you, and they're very small. Okay? Then you have the LAN. The LAN is the most common in a computer lab. A lab, for example, will have a LAN in an office, in an apartment, in a building, you know, a Wi-Fi that you have in your house. You can make a LAN out of it. So we'll be doing that together to connect the LAN. So a LAN is a local area network. It's kind of small. We're talking about within a room, maybe apartment, maybe a floor, and sometimes could go across a campus, multiple buildings. So it's still small. We're talking about a maximum of 1 kilometer almost, you know, 1 or 2 kilometers, not much, you know. So this is what we call a LAN. Now we go a little bit bigger, we become metropolitan, as you expect, metropolitan meaning city. So within the city, we're talking about 10 to 20, maybe 50 kilometers. So around 10 to 50 kilometers. That's what we refer to as a MAN. Again, it could be a small town, a small city. Again, we're talking about diameter or radius. So this is kind of estimate, of course. But again, you say, why do we care? Why do we need to classify them? Because if you are a PAN, what will change? What will change between a PAN, a LAN, a MAN? From the components of communication that I've talked about before, what will change from one to the other?
Professor, if you're speaking, we can't hear you.
You can't hear me now?
No,
Can
we
you hear
can
me?
hear you.
No?
We can hear you, sir.
You can hear me. Okay, somebody couldn't hear
I,
me for
I
some
can
reason.
hear you.
Thank
I
you,
can- I-
Fatima. You can hear me, right?
Yeah, I can hear you.
Okay, thank you, thank you. So back to this. So buddy, if you cannot hear me, maybe it's something from your side. Oh, he cannot hear me. How can
Now
I
I can
talk?
hear you. Now
Oh, now
I
you
can
can hear me. Okay, okay, good, good. Okay, back to this. So what was I saying? I'm saying what changes from the PAN to the LAN to the MAN to the WAN? What changes from the components of telecommunication? What changes? What are the components of telecommunication that I mentioned before? We have the sender, receiver, the message, and all this. What will change? Why do we care to classify the networks? What will change eventually?
The population
The
size.
protocol?
The protocol, 100%. Bonus point for you. The protocol, of course.
Wow.
The protocol that we use for PAN is different than that we use for LAN, is different than that we use for MAN. And we'll talk about many examples later on. Of course, the protocol will change. So I'm not going to use, for example, HTTP application protocol to use this protocol in the LAN. That would be very bad. I'm not going to use the FTP in the LAN, for example. These are protocols you know, so that's why I'm using them. But just an example. Of course not, everyone have their own protocols based on their size, because it really makes a lot of assumptions and so on. So one size doesn't fit all. They're all networks, but their sizes will kind of infer what kind of protocol we'll be using. Okay? Very good. So these are the different sizes. Again, LAN, MAN, WAN. Again, wireless, obviously, typically wireless is a LAN, wireless LAN, like Wi-Fi in your house, it's a LAN. Obviously, mobile networks, if you talk about cellular, obviously we're talking metropolitan, like within a city. Again, it could also be bigger. So yes, these are the different networks, but the sizes, typically the most common are LAN, MAN, WAN. This is what we use all the time. We say LAN, is it a LAN, is it a MAN, is it a WAN? Okay? So let's go over them real quick. So LAN, they're small. They're high data rate. Again, obviously this is the minimum. So talking about LANs, we're talking about a minimum of 100 megabit per second, minimum. But again, we're talking about 1 giga. So gigabit Ethernet is 1 gigabit per second. So 1 giga. You could, in the local area network, you could send 1 gigabit per second. Again, we call it gigabit Ethernet. You could go 10 gigabit per second even. Okay, so they're super fast, of course. Why super fast? Because they're super small. So LANs are very, very fast. Again, if you're copying a file, 10 gigabits, you can do it in 1 second. Imagine, that's huge. Okay. Again, low cost, because again, they're small. Typically in a LAN, we said the transmission technology that we use is broadcasting because we're using a bus. Okay. And because we are restricted by size, what does that mean? It means that we can use a LAN for testing purposes. Meaning I could test other protocols in a LAN because I'm limited with size, so I have a lower bound, an upper bound. So if I want to do a protocol for the internet, usually we can test it on the local area network first, because I could control the size. So controlling the size allows us to use a LAN as a testing environment for other protocols. Okay, so typically we do use in broadcasting. And as I said, the minimum is 10 to 100 megabit per second goes. This is what we refer to as the Ethernet. This is what we refer to as the Ethernet. Okay, Ethernet. And then obviously it could go up higher. That's what the LAN is. So something to note, we need to know units, very important. We need to know units. So this is megabits per second. Mega, the small letter B is bits. Small letter B is bits, of course, per second. And the capital M is mega. Mega meaning, for you to remember, capital M is mega. For you to remember is million. Million. So see the M, so you won't forget this anymore. Mega million, meaning million bits per second. A mega is a million bits. Okay? Capital B is a byte. Capital B is a byte. And 1 byte is how many bits, guys? 1 byte is how many bits?
8 bits.
8 bits, thank you. 1 byte is 8 bits. So make sure when you're looking at the unit, you know, is it a megabit? Most commonly it's megabits, but you never know, somebody might put megabyte per second. So make sure that, it's megabyte, so I multiply by 8 because 1 byte is 8 bits. So a megabit, as I said, mega, M is million. This is how you don't forget this. Of course, I'll show you now the transformation. Okay, so mega is million. When we talk about it in terms of networking, a mega is a million in terms of networking. In terms of data storage, in your hard drive, in case you don't know, in your hard drive, a mega is not a million. When we talk about storage, computers use binary. Computers use binary. So if I'm talking about a mega in computer storage terminology, it's definitely not a million. You see the difference? In networking, they agreed on it. They said, you know what? I don't know if I have a chart. I don't have a chart here. Let me talk about it here. Okay. In storage, in computer storage, again, database storage even, we have a bit, you know, a kilobit, and we have a megabit, right? And of course, you have a gigabit. And you can keep on going. You have terabits and so on. But for you to know that in storage, 1 bit is 1 bit, of course. 1 kilobit in storage is how many bits? Who could tell me? Is it 1,000 bits? A kilo, is it 1,000 bits?
I think it's 64.
What is it?
64.
No, kilobit. It's almost 1,000, but it's not exactly 1,000. How much? Come on. 1. You should know this.
2024? No?
1024, of course. Which is basically 2 to the power. Anybody?
8? No, 2?
2 to the power. It's famous. 10. Okay. So again, you guys, your major is what? Computer science, right? Just confirming. You guys are mostly computer science and IT? Yes? Nobody's answering anymore. Can you still hear me?
Yes, yes.
Yeah,
Okay,
my
good,
math.
I like that.
my
Are you
high
computer
school
science?
math.
We don't know. Okay. So that's fine. So 1024, you need to know these. These are kind of the ABCs of computers. I'm very surprised you don't know this. Okay. So yes, a kilobit is 2 to the power 10. A mega is 2 to the power 20. You see? 2 to the power 20 bits, which would be about, you can see it here, 1,048,576 bits. and a giga to the power 30, and you can keep on going, you know? So this is when we talk about storage. However, in networking, they came and said, you know what? What's the big deal, okay? Let's not go with the same convention as they have in the computer storage. They went and came and said, you know, we have a bit. And now I'm talking about networking. Networking. In networking, when I'm talking about these units, they said we're gonna make it easier. So we have 1 bit, we have kilobit, the same thing. When I'm sending and receiving it, not when I'm storing it, when I'm sending and receiving it. A megabit, a gigabit. You need to know this, please, huh? So, really quick. So you can see 1 bit is 1 bit, of course. A kilobit is how many bits in networking, guys? I just said it. It's 10 to the power.
2 to the power of 10.
10?
No, 10 to the power of a kilo. Kilobit is how many bits? 10 to the power of what?
3.
3. Thank you. 10 to the power of 3. Then a megabit is 10 to the power
4.
oh,
7.
multiplied by 2.
6.
6.
6.
Okay, because a megabit is 1,000 kilobits. A megabit is 1,000 kilobits. So basically, it's double this. So it's 1,000 times 1,000. And a gigabit, as you would expect, it's 1,000 megabits. So it's a 10 to the power 10 to the power
12. 12. 12?
No,
Or is it 9?
it's 1,000. So you kind of 3.
9.
9.
Okay, one more time. Each one is 1,000, the one before it. A kilo is 1,000 bits. A mega is 1,000 kilobits. So 10 to the power 3 times kilobit. And a giga is 1,000 mega. Again, this is in networking, huh? There we used to multiply by 2 to the power 10. Here we multiply by 1,000. That's the difference, okay? So make sure we know this convention. We'll be talking about it more next lecture. But I want to make sure we know it by now so we don't waste time on this moving forward. Okay, very good. Again, take a snapshot of this in your head. Very, very important, okay? Let's move on. So we can classify, again, examples. Oh, yes, examples of LANs. We're still talking about local area network. We have the IEEE 802.3. This is the protocol, the standard. Okay? We call this the Ethernet. Ethernet bus, you could see, they're connected to a bus. They're all connected to a bus. This black thing is called a bus. All of them are connected to it. The protocol is called IEEE 802.3, or something we refer to, this is important, CSMA, you know, which is what stands for Carrier Sense Multiple Access. One more time, CSMA is Carrier Sense Multiple Access. What does it mean? Is carrier sense meaning I'm sensing before I send. Suppose this guy A wants to send, right? This is a LAN. They will typically broadcast it, but before they broadcast, they want to make sure that B, for example, is not also broadcasting. Because if that is the case, what will happen? If A wants to send and not check before sending, and B wants to send and did not check before sending, what will happen between A and B messages? What do we call it? What will happen? What will happen? A collision. What is a collision? It's when a message from A collides with a message from B. In order to avoid this collision, what we need to do is do something called sensing. one of them needs to sense the medium and see, is there anybody else sending? If there is somebody else sending, they will simply refrain from sending. They just wait and then send later. That's what we call carrier sense multiple access. Something important in order to avoid collisions. Okay, so anyway, let's go back to the picture. So we have examples of LANs. You can see this is a local area network, computers connected to a server, or another example using not a bus. What am I using here? I'm using a star technology, a hub. This is what we call a hub. You know, similar to what you have in your house, right? Could be wired, could be wireless. Are you guys still with me? Are you still with me, guys?
Yes, Professor, I'm here.
Okay, excellent. Thank you. Thank you. So back to this. So we have a hub here. Example of this is what you have in your house, right? With Wi-Fi. This could be easily a Wi-Fi network where you have a LAN, a wireless LAN, connecting multiple computers together. You can easily do that. Or it could be like in an office, for example. This could be an office example. Most offices, when I plug my computer to the wall, this is kind of the wall socket. This is called Ethernet. Again, Ethernet is this blue cable, the blue cable that you see, and you plug it behind your computer and you plug it to the wall. That is what we refer to as an Ethernet cable. Okay? Again, it could be wireless, as I said. You could see wireless LAN. So you have a wireless router and you have computers connected to it. Again, you could also have something called an ad hoc computer, an ad hoc network. You know, ad hoc networks are very, very important because we don't require a base station. We don't require a router. You guys know that? You know that you could connect your laptop to another laptop in an ad hoc mode? Meaning I could send from this computer to this computer without using internet, using ad hoc communication, directly connecting them to each other. You know, it's very similar to like a mobile hotspot when I have my phone connecting to your phone, you know, without using a router, without using a switch. Directly, they're connecting to each other. So that's called ad hoc. Again, obviously, Bluetooth is a good example as well. We could use it with using the normal Wi-Fi, where we connect it without using a switch. In this case, I'm using a router, right? I'm using a switch, a hub. Or you could connect them immediately to each other. So ad hoc, this is called ad hoc mode. Very, very important. And especially, this is very useful, you know where? It's useful in IoT. What does IoT stand for? Bonus point, quickly. I said it last time. IoT stands for IoT. Hello.
Internet of Things.
Internet of Things. Did you Google it or you knew it?
I knew it.
Okay, very good. Bonus point for you. Thank you. So, Internet of Things, of course. Everybody's talking about IoT, guys. Come on. IoT, something very, very important. So, IoT is where sensors are doing stuff connected to each other, you know, to do a specific objective. So, Internet of Things is very important. Hence, it uses ad hoc communication. So, it uses ad hoc communications. Okay? Very good. So let's move on. So can we say mans? Of course not. We of course yes. Can we say mans? Can we say mans in English?
No.
Yeah. Why? What does it stand for?
Man is, if there was a comma, I think.
No. Mans. In networking, what does it stand for?
Metropolitan Area Network.
Yeah. So mans would stand for metropolitan area networks, right? So we don't mean men. Of course, we're not talking about men here. We're talking about metropolitan area networks. Okay, so it's fine. So what does it mean? We said metropolitan area networks. That's the plural of a man. Again, as we said, medium size. We still don't have switches. So they're connected directly to each other, typically. Again, example of a MAN is a cable TV. That's the easiest for you to remember. So remember, for Ethernet, it was IEEE 802 point what? For LAN. For LAN, it was IEEE 802 point what?
3.
3. Thank you so much. That's what we refer to as Ethernet. When we talk about MAN, we talk about IEEE 802.6. Again, IEEE is the Institute of Electrical and Electronics Engineering. This is what IEEE stands for, huh? Just for you to know, which I'm a member of, by the way. I'm a member of this committee or this society. So IEEE, Institute of Electrical and Electronics Engineer. So this IEEE 802.6 is what we call DQDB, Distributed Queue Dual Bus. So again, what does it mean? It's a queue that's distributed, and we have 2 buses, not 1 bus. In the LAN, we only had 1 bus. Now we have a dual bus, which is basically going in 2 directions. Maybe I have a picture now. So a good example of a MAN is the cable system. You know, if you're getting TV cable to your house from a source in Dubai or a source in Abu Dhabi and so on, this will be typically a MAN, a metropolitan, but they're connected to all the houses in a very interesting. Let me show you a picture. This is a good picture. You can see, example, this is a queue. You can see 1, 2, these are all buses, right? So think about these as bus, similar to a LAN. So I have bus, 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 bus. They're all connected to one connection. Let's call it a end-end. Again, maybe internet and antenna. And this is feeding them. It's feeding them like this. So this is what we refer to as a typical metropolitan area networks. Again, multiple queues, as you can see. So DQ, DB, for example. You know, we have 2 buses and distributed queue. Distributed queue dual bus. Okay? Again, one more time, metropolitan still don't have any switches. Of course, it's a bit slower. It's a bit slower than a LAN because it's a bit bigger. It's not as fast as a LAN. We still don't have switches because this is where we talk about WANs. Okay, these are example of networks of a MAN where we draw them. Very important. You could see this is a metropolitan area network connecting A, B, C, D, as you could see. And if I zoom in, I could easily zoom in to one of the network, for example, A. Just show you an example. So you could see, you could typically connect, this is one network connected to maybe another network here. We'll talk about this later on. You know, connected to another network, for example. So I could zoom in or zoom out to the networks. Okay. It's another network. So this is a metropolitan area network A consisting of subnets A, B, C, and D. As you can see, this is A. We call this subnetwork A, B, C, and D. A, B, C, and D connected to each other form the big network A. Okay? And A could be part of another network. So we could expand. So you could zoom in and zoom out to these networks. And this is what we call topologies. I'll talk about it in a second. Okay? So this is metropolitan area network. Okay? We talked about the local area network. And the next one, as you would expect, is the wide area network. So these are larger in size. They're larger in size. Typically the largest. Of course, you would expect low data rates. So low data rates, again, minimum, typically 1.5 megabit per second, you know, in some countries. Of course, now we could get to maybe, you know, depending, but you could go to 100 megabit per second easily. Most of you maybe have 100 mega, 1 giga. It's obviously far stretched because of many criteria, but we're getting there. We're getting to 1 gigabit per second download rate, you know. But typically, yes, wide area network. ranges from 1 megabit per second to 1 giga maybe, but typically they are the slowest because they're the biggest, because they depend on many factors. They're definitely high cost because you're talking about millions of dollars. Transmission lines, this is where we start talking about switching elements. Switching elements is basically switches, routers, hubs, and so on. As you see here, I said, when I talked about demand, I explicitly mentioned we have no switching elements yet, you see? We're still kind of trying to connect them without major switches. Now with the WAN, we need to have a switch in between because they're very big. And these switches run hundreds and hundreds of kilometers. Okay? So back to this. Sorry. So we have switching elements connecting the transmission lines together. And a very good example is the internet. And this is a good depiction of what a WAN is. So we have the sender here, sending host. You have the receiving host. Again, there is a process in charge within the host itself. I'm going to send. As you could see, this is what we refer to as the subnet. Very important. The subnet is the collection of switching elements, switches. We'll talk about the different kinds of switches, but again, typically routers, these are huge devices, not like the ones you have in your house. These are not actual routers, the ones you have in your house. They're typically hubs. They're not a physical router. Router, we're talking about things that will send information over hundreds of kilometers. This line that you see here, we're talking about typically 100+ kilometer. Okay, so this is the subnet. This is the thing allowing a computer to connect to another computer or another server, you know, using a subnet that uses a routing protocol. So you can see C makes a choice to forward the packet. So we go from the sending host. Let's do it again. We go from here to A goes to C goes to E, and then E goes to the host. So my question to you, how did we know to go from A to C and not A to B? Who could tell me? What did we use? What did we use? Hello? Yeah?
Switch.
No, what did we use to know who told us don't go A to B, go A to C? What do we call it? Yeah?
An algorithm?
Yeah, what kind of algorithm?
The routing one?
Routing algorithm, yes. Bonus point for you, thank you. The routing algorithm, we said the routing algorithm decides what is the optimal path. Hence, it knew the best path to go is A goes to C, not A goes to B, based on traffic, based on many other criteria. Okay? Very good. So this is what a WAN is. Again, we have wireless and mobile networks. Again, obviously, that's the fastest. We're talking about cellular, we're talking about Wi-Fi, WiMAX. All these are common wireless examples. So again, wireless network, you could see connected using ad hoc or using a base station. So we could have Bluetooth configuration. So wireless is very common, including cellular communications, including 5G. So the 5th generation, which I'll talk about later on as well, or you will be doing some seminars on this, okay? So again, even in airplanes, I think you know now we have internet, right? We have internet, we have telephone connectivity on an airplane. That's very interesting. You are over there and you are connected to the internet. So you could have a flying LAN, a flying local area network, or even internet connectivity, okay? Excuse me. So you could have a home network connectivity as well, you know, like a smart system, entertainment system, telecommunication, appliances. So all these are common things that you could have in your house, okay? So we could connect these together. So when you talk about the internet, this is a very good example of the internet, a network of networks, okay? So next week, I'll make you watch a nice video about the internet. You would really understand how it works. But typically the internet is a network of networks, okay? As you can see, network 1 connected to a network 2, network 3, 4, 5. These are all networks. If you zoom into them, you will see this is kind of like, it could be a bus. Sorry. This could be a bus network. Okay, this could be, for example, a Wi-Fi network, as you could see. So all these are networks connected to each other, forming a very big network of network. Again, the G is typically a gateway. Gateway meaning going from one network to another. And we will have switches in between, we'll have hubs, we could have routers in between, and so on. But this is a very nice picture for you to visualize of how the internet works. Okay, we'll be talking about it more, don't worry. But this is a good start. Tells us we could also classify networks by topology. So we could classify them based on the technology, which is broadcast, multicast, or unicast. We could classify them based on their size, which is basically PAN, LAN, MAN, and WAN. And we could also classify them based on topology, which means how they are connected. Okay, we already talked about some of these topologies. The first one is the bus topology. As you could see, we already talked about it. Where do we use the bus topology? Where do we use the bus topology? In what kind of network? Typically? In what kind of network?
A bus topology.
Yeah, I know. Where do we use the bus topology?
Off and home.
Yeah, what kind of
Oh, where
network?
do you
What do we
use
call
it?
it?
Wide area network.
A local area network.
Of course, a local area network. Guys, wake up, please. What's happening? It's Saturday. Yes, a local area network. Bonus point for you. Thank you. So a local area network. Of course, we said that in an office, as you said, but the network is called a LAN, a local area network. Again, very easy. You could see these are computers, they're hosts. In a bus, we can send to each other, as you could see. We broadcast on the bus, and one of you would receive it, everybody else would ignore it. We could have a repeater, for example, connecting two buses. This is one bus, bus 1. This is bus 2. Typically bi-directional flow. Bi-directional flow means I could go in both directions. So I could go this way or I could go this way. Okay, obviously, what could happen in a bus, we said? What could happen? What could happen when we're sending and receiving? What could happen? What could happen when I'm sending and receiving?
Collision.
Collision.
Oh,
So
yeah.
we could have collisions, meaning they will hit each other. These messages will collide. Again, a message is not a physical message. It's a bunch of bits, right? Zeros and ones. It's signals. So my signal could interfere with your signal. Therefore, I will have a collision. Okay? Which means I need to resend it. So yeah, that will happen a lot in a bus. This will slow down the bus. This will slow down the bus because of the collision. Okay? You could slow down the bus because of collision.
I'm sorry, some people are being very responsive, but they can't use their mics. Like they're in the chat. They're being very quick, though, when you ask
Okay.
questions.
So maybe that's why I'm not seeing it all the time. It's fine.
Yeah.
Okay. Okay, good. So let me try to see the chat. Okay, yes. Now I'm seeing the chat. Okay, thank you. How do we stop the collision? Okay. We stop it by using CSMA, Fatima. CSMA. Remember CSMA? What does CSMA stand for? I just talked about it a second ago.
Case.
What does it stand for?
Sector. Something access.
Sorry?
Center? Is it center?
Yeah. Carrier,
Oh,
sense,
carrier.
multiple
Carrier sense multiple access.
access. So this is an algorithm. We'll talk about more later on, but carrier sense multiple access is what allows us to avoid collisions. Yes, good question and answer. Okay, very good. I like it. Topology, good. So one more topology is something we call the token ring. The token. So remember, in the bus, it's bidirectional. Collisions could happen. Therefore, it could slow down the bus. So because you're broadcasting to everybody, and it's only useful when it's a small. Also with the bus, let me go back to the bus a little bit. In the bus, if, for example, this fails, if this computer stopped working, would it affect the bus? Would the bus be affected if this computer stopped working? Can these guys continue to work? No, it's fine. Yeah, if this stops working, everybody else will continue working. No big deal. You know, we're not depending on one of them. But if the bus fails, the problem, if the actual bus fails, if I cut the bus, if it fails, what will happen to the whole thing? The whole network will go down if the bus fails, because they're all depending on this bus. Okay? Because indeed, Muhammad, it is the backbone. Yes. So if the bus fails, the whole thing is dependent on it. Okay?
Professor,
Yes.
what's the repeater?
Repeater repeats. You know, I mean, some of you have repeaters in your house. It repeats a signal. For me to connect these two networks together, I usually need a repeater or a gateway or some kind of a switch that will take data from this. Suppose this guy A wants to send to C. To send, A has to go to the bus, go through the repeater that will repeat the signal, comes here, and goes all the way to C, you know? So a repeater allows us to connect multiple networks together. Typically, as the name sounds, it repeats the signal, whatever you send, okay? Excellent. So, are we good? Let's move on.
Yep.
Professor,
Thank you. Yes, tell me.
I thought bus topology was known for that if one network goes down, there's still others. So that if one goes down, everything is not gone. So
No. Who said that? A bus is the opposite. If the bus goes down, everything goes down. But if one of the computer fails, if the computer fails in a bus, yes, everything else continues working fine. Okay? Cool? Okay.
yes, Professor, thank you.
Thank you. So the ring topology now, again, there it was bidirectional. Here, it's unidirectional. A ring is unidirectional. So I still have them connected like this, as you can see. So we sometimes call it token ring. So if you have the token, you can send. But typically, suppose this is A, this is B, this is C, this is D. So a ring topology, so if A wants to send to D, as you see, it has to go like this, unidirectional, okay? It cannot go like this. No, it has to go like this, until it comes here. So a ring topology, as you could see, they are in a ring. It looks like a ring. And if anyone wants to send, suppose this is A, wants to send to E, it goes like this. You see? If A wants to send to X, it cannot go like this, cannot go like this. No. It has to go all the way like this. Okay? To solve this, what we can do is we can have two rings. You know, some people might have two rings. Ring 1 and ring 2. One to go this way and one to go the other way. Okay, that's what we call a bidirectional ring. So this is typically a ring is unidirectional, but you might fix it by allowing two rings to be on top of each other. Hence, we refer to it as a bidirectional ring. Okay? Again, it is interesting. So what's the, you know what? Let's do a quick example here. You know, what's the best case scenario? Be quick. It's how many times I need to go. If A is sending to, what's the worst case best case, worst case, and best case. Who could tell me? Let's do it now. I'm not gonna do all of them. In the tutorial, you'll do more. But for me to explain it easier for you, what's the best case scenario that could happen?
A sends to B,
B, yeah.
Yeah, where is B?
just
There-
next to A on the right.
Yeah, so how far is it? How many links? One,
Only one.
right?
One.
Only one. This is the best case. Thank you. Best case is one. What's the worst case?
A sending to H,
What is H?
the one to the left of A.
Here.
Yeah.
Okay, you're smart. You're smart. Bonus point for you. So, and again, assuming the size of this is n, I have n nodes or n computers. So, what's the worst case? If A sends to H, what's the worst case?
Goes from A to B to C to D to H.
Yeah, how many? I said n. And how much? So, the worst case will be
7 links?
n minus 1, right?
Oh.
N minus 1, right? Think about it. You could do it in your head for 1 second. So if n was, suppose I have 10 computers, the worst case is I have to go 9 times, right? Worst case, I have to go 9 times. If I have 10 computers, if I have n, I have to go n minus 1. Guys, you need to be comfortable with these thinking. This is very important. When we are doing networking, we need to understand how to design. We need to become engineers of our networking diagrams, Very, very important. So again, I want you to start thinking about this. So yes, if it is unidirectional, now if it is bidirectional, it's a different story. If I could go in both directions, suppose I could go in both directions, guys. I could go like this, or I could go like this. So what do you think the worst case scenario would be?
The one, the bottommost one to A.
Which is what? This guy?
E, yeah.
This?
Yes.
Okay. So if I have n nodes, what's the worst would it be? If I have n computers, what's the worst that it could be?
4.
No, there's no 4.
Sorry,
There's no
4,
constant.
no,
I said
N is 4. N is 4.
No. What n is 4? Okay, n over 2. Yes, somebody put it on chat. N over 2. Yeah, bonus point for Vida. N over 2. N over 2, of course. Yes. Typically the ceiling or the floor of it. But yes, n over 2. You can see these are clever things to think about. Think about these. Think about them. So let's move on.
Professor.
Okay. So one more topology, the tree topology. Again, the tree topology, we saw it before, right? Where did we see something like this before? In what example? When you're talking about different sizes. Where did we see it? A man. Yes, Veda. A man. This was a similar example for a man. Where we have multiple queues or multiple buses. Bus, connected to a head end, and then if somebody here wants to send to somebody here, he typically has to go through their bus, go through the head end, and then come back to this guy, So yes, we've seen this picture before, a man, as Vida said. Okay, so yes, example of a tree is I have a root. We call this the root. That is controlling everything. So these are leaves, and again, every computer is connected to what at a specific level. They could talk to each other using the bus, but if they want to go to another level, they have to go through the root, which is the junction, the head end. Okay. Another one, which is the most common, is the star topology. The star topology, where I have a switch connecting these together in a star. So basically, again, A, B, C, D. So if A wants to talk to B, A has to go through the switch and then go down to B, So again, this is good. However, the bad thing about this is what? What's the bad thing about the star topology? If the star fails, what will happen?
The whole network fails.
The whole network fails. So it's very centralized. It's centralized. It's all depending on this star. You know, like the router in your house. If you turn it off, all the computers are gone, you know? So,
That's just like the bus, right?
sorry?
It's just like the bus.
Kind of, yes. But the bus is a bit different because, yes, you could think about like a bus, yes. The star like the bus. But the bus, everybody broadcasts to everybody. In the star, no. I only send to the star and the star sends it back to the computer that I want. Okay, this is how the star works. So if A wants to send to B, A would not send to C and D also. In the bus, no. A would send to everybody. Okay? Very good. So let's move on. So that was the star topology. Again, example of a star topology I told you is the Wi-Fi, you know, the wireless Wi-Fi that you have in your house. It's a star topology. As you can see, we have one access point and multiple computers connected to it. Okay? So let's go back to these, a quick review. So what is this? Let's do a quick review. What kind of topology is this?
Bus.
Bus topology.
Bus. This is what?
A ring topology.
A ring
Ring.
topology, a token ring. Okay? And yeah, if you can leave if you have to. We're almost done anyways. Okay? Let's move on. So let's do these real quick. So what is this?
Star.
Topology.
Star topology.
Star topology. What is this?
Ring.
Ring. This one.
Tree.
Tree. This one. We didn't talk about this yet.
Ring.
This is where everybody's connected to everybody.
Internet.
No,
WAN.
it's a mesh.
WAN.
Of course, not the internet. It's a mesh topology. This is
Oh,
what we call a mesh. Everybody's connected to everybody.
topology.
Okay, or sometimes we call it a complete network. A mesh or a complete network. And what is this?
A ring and a star.
Married ring
It's
star.
two rings, right? We call it, I mean, it's two
Right.
rings, intersecting rings. Intersecting rings. Okay? But it's two rings intersected here. And finally, this one is a random. It's a random.
Random topology.
It doesn't mean anything. It's just everything combined to everything. Okay? Very cool. Very cool. Again, make sure you're comfortable with these. Again, obviously a mesh. What's good about the mesh? Everything's connected to everything. So if a link goes down, what does that mean?
The network doesn't fail and it's the same.
Exactly. I always have alternatives. If this goes down, I still have another alternative because everything's connected to everything. The problem with it is very costly, right?
Yeah, it's very, very costly.
Very costly, but still very fault tolerant, you know?
How
It's
is
good
it
for
costly?
fault tolerant.
How is it costly?
Yeah, it's very costly, yes, because I have many, many links. And you could do the calculation, see how many links do we have. We can do that. Maybe in the tutorial, you can do that. Think about it. If I have 4 nodes, you know, maybe in a square, and I have a complete network, how many links do I have? Look at it. This is a typical complete network, right? Where everybody's connected to everybody. If it's 4, A, B, C, D. If I add a new network, if I add a new computer here, how many links extra do I have to add? So everybody needs to be connected to it, right?
4 links extra.
Only 4?
Yeah.
Yeah, A to E, B to E, C to E, and D to E, right? Exactly. So if you think about it, as we grow, how many we keep on adding, it becomes very complicated every time I add a new node. So try to visualize these and understand them, okay? Professor, mesh is the LAN? No, of course not. Mesh is not the LAN. A LAN is the bus. A bus is a LAN. This is a LAN. This is a LAN. This is a LAN. Okay? A mesh usually we don't do meshes. We only do meshes when we're doing some kind of extreme testing for planning and purposes, but this doesn't exist. I mean, we usually don't do it in live. Unless, I mean, I don't know why we would do it. It's gonna cost too much money. Okay? Especially if it's a big network. Okay. Very good. Yes? I think we got these. So this is random or irregular. Random is fine. So again, you have point to point, point to multi-point. So you could see here a point connected to another computer, or you could have multi-point connections. Again, this is a mainframe where I have multi-point like a bus. Okay, these are more pictures just for us to make sure we got these. Again, this is like we already talked about this, right? A metropolitan example, or here a hub with multiple buses. You can see bus 1, bus 2, bus 3 connected to a physical hub. That's another example. Again, this is a tree topology or a star topology. To be more specific, it's a star. Again, what does this mean? You could see here, the backbone is a star. The backbone, okay, is a star, right? This is my backbone. It's a star, basically one computer, a star, or one hub connected to 3 different things. This is a star. That's my backbone. And then every one of my networks is what? Every one of them is what? The things connected to the star. It's what kind of topology? It's a bus. Thank you, Meta. It's a bus. So the typical exam question, we'll do that in the tutorial as well, is draw a network where I tell you what the backbone is. I could tell you the backbone is a ring, or the backbone is a star. If I tell you the backbone, the first thing you would do is draw the backbone, like I did here. So here it's a backbone is the star. I drew it. And then it told me, every network in your, every sub-network is a bus. Then I come and say, okay, this is a bus. This is a bus. This is a bus, and this is a bus. Okay? Does that make sense? So this is, as you could see, a star backbone. Yes, it is official, of course. We use that a lot in networking. Okay, so a hybrid topology, as you could see, in this case, I have a star backbone with 3 bus networks. So this is a typical exam question. I tell you, draw a star backbone with 3 bus networks. This is a good example. Okay? So here we have, for example, 12 computers in a hub, as you could see, all of them with 1 hub. So this is a typical star topology. As you can see, all of them connected to the hub. All 12 computers connected to the hub. Okay? So this is a local area network with all 12 computers connected to the hub. So here we have a switched wide area network and a point-to-point wide area network. So you can see here, this is a wide area network, a computer connected to a modem, another ISP connected to a modem, using point-to-point, so directly connected to it. As we said, we have point-to-point P2P connected to it. So this is an example. In this case, it's switched. What does it mean? Let me just show you. So I have A, wants to connect to B. It goes through multiple networks. So this is one network connected to another network, connected to another network using switches, connected to another network until I come to B. So these are all networks. This is what we call a switched WAN. What is a switched WAN? Meaning multiple networks connected to each other using switches. Okay? Which our devices will be talking about later on. Very good. So here we have 4 WANs and 2 LANs. Very cool. I like this. So here we have a heterogeneous network with 4 WANs and 2 LANs. You can see this is a local area network in a hub or a bus. So we have one in a bus. This is a bus. And here a hub or a star topology. And then we use a router to connect point-to-point to another router to connect to 4 WANs. As you can see, 4 wide area networks which are connected with each other in a switched WAN. and then I go all the way maybe to the president, to wherever you want to go. It's a good design of a heterogeneous network. When I say heterogeneous, this is opposite to homogeneous. Heterogeneous meaning I have a mixture of LANs and WANs with different topologies connected to each other. This is what heterogeneous means, okay? Okay, very easy. If I tell you, draw a network with 2 LANs and 4 switched WANs connected to a main server. I say easy. This is the first LAN. This is the second LAN. I need some kind of a device. It could be a router, it could be a switch, it could be a bridge. Again, router is fine. Connected to this whole switch LAN network. In this case, it connects 4 of them to each other. Okay? Okay, again, when you talk about the internet, usually it's organized in a hierarchy. So we have an ISP again, internet, service, service provider. Okay? So the internet service provider, these ISPs, again, we have regional ISPs and you have national ISPs. Every country has these. So within the region, we have multiple ISPs connected to each other. And within the country, we have national ISPs. Again, these are usually organized in a hierarchy, as you can see. So we have regional ISP connected to each other to form a regional, connected to each other to form the national. Again, national ISPs also are connected to each other to form an international ISP, okay? So this is something to keep in mind. Not very important at this stage, but just know that also the internet service providers are connected to each other, okay? Finally, just to finish today, we have the store and forward, which is basically another word for point-to-point. So we already talked about point-to-point. Point-to-point, as I said, it's what we use in the internet. If I want to connect a computer to switches and so on, we connect them in point-to-point. This is what we call P2P, where we came about routing algorithms, something we started the lecture today with, right? So another word to it is something we call store and forward. Why store and forward? Because if this is a switch going to B, right? If I'm sending something, B would receive it, will store it first in the queue. It will have a queue. It will store it in its queue. And then what? After it stores it, what does it do? After it stores it, what does it do?
It will
Store
forward.
and
It moves it forward, it whatever.
yeah, we call forward. We forward it. And hence, this is why some people call the point-to-point network is basically a store and forward network, okay? So we'll be talking about it more next lecture a lot. But for now, remember, a store and forward network is a network where we have routers storing and forwarding to the next router based on an optimal algorithm. Next week, it's all about discussing the performance of a network. It's very important to understand how different networks perform. Talk about latency, talk about end-to-end delay, talk about transmission time, all these things, something called queuing delay as well, processing delay, propagation delay, in order for you to understand how things work when messages are being sent and how can we optimize it. Okay, guys? Are we good? So we are officially done, unless